In the field of physics, it is quite uncommon for a giant to challenge a theory that many people have taken for granted. The well-known Penrose singularity theorem might find itself in such a situation according to a recent article written by Kerr if our interpretation is correct. To make a lengthy story short, it is possible that the terrible singularity known as the black hole has disappeared. Welcome to Spaceverse, your cosmic companion in unraveling the mysteries of the universe. In this channel, we dive deep into celestial wonders, interstellar adventures, and the latest space news. Join us as we explore mind-bending theories and groundbreaking research from leading astrophysicists and cosmologists. Don't miss out. Subscribe, hit the bell icon, and let the cosmic adventure begin. It wasn't until several centuries after gravity had already been established that Isaac Newton made the discovery of the law of gravitation. Everything that had been a mystery up until this moment, such as the reasons for apple drops and the motions of the heavenly bodies, became a great lot closer to being known. This includes the factors that cause apple drops. In contrast, the discovery brought to light an even more fundamental mystery. It raised the prospect that the gravity of a sufficiently large object may generate an event horizon, which is a barrier from which light cannot escape. This is a surface that cannot be penetrated by light. Due to the fact that this discovery brought to light the paradoxical nature of black holes, physicists are still having a difficult time making sense of the phenomenon. The modification of Newtonian gravity that Einstein proposed appeared to verify the theoretical possibility of the black hole. This was in addition to the fact that it revealed something that physicists found even more difficult to explain. One of the first general relativity solutions, known as the Schwarzschild solution, provides a hint that there is a singularity at the very center of the black hole. The theory of general relativity and the theory of quantum mechanics are in direct opposition to one another when we approach this hypothetical limit of density and gravity. The two most comprehensive explanations that we have for the physical universe are plainly in conflict with one another when applied to the singularity scale. There were a great number of scientists who felt a great deal of anxiety over black hole singularities. What made it much more difficult for them was the fact that in 1965 the British physicist Sir Roger Penrose demonstrated that singularities are an unavoidable consequence of general relativity. In the year 2020, he was honored with a Nobel Prize for his Penrose singularity theorem, which asserts that the existence of an event horizon is contingent upon the presence of a singularity. The singularity theorem has a number of important implications, one of the most important of which being the demonstration that quantum physics and general relativity are fundamentally incompatible with one another. Because the singularity was a nightmare that was conjured up by naive scientists in the 20th century, the only way to solve the conundrum of the singularity would be to develop a more comprehensive theory that incorporates both quantum mechanics and general relativity. If this is the case, then the singularity would simply disappear in this theory. A glimmer of optimism, on the other hand, has only recently appeared from a source that was previously considered to be unexpected. It has been proposed in a study that was conducted in December by Kerr, who is widely considered to be one of the most well-known black hole theorists in history, that quantum physics is not required in order to escape the singularity of the black hole. Before moving on to this brand new discovery, let's first review the Penrose singularity theorem and refresh our understanding of black holes. Only after that will we be able to proceed with this new discovery. Afterwards, we might be able to ascertain whether or not Kerr indeed succeeded in removing the singularity. The first thing to note is that Roger Penrose did not demonstrate, at least not in a direct manner, that singularities do in fact exist. As a result of his research, he demonstrated that the final destination of every spacetime passage is a black hole. The path that any item must take in order to travel through spacetime, while being subject to gravity alone, is known as a geodesic. By traveling along this spacetime path, the total distance traveled both in terms of space and time is reduced to the greatest extent possible. Prior to the announcement of the Penrose singularity theorem, it was commonly assumed that geodesics could continue on indefinitely. It is possible for a geodesic segment to represent the path of an item, such as a ball that is thrown in a parabola, for example. Nevertheless, the geodesic can be followed in both directions. You have the option of traveling forward into spacetime indefinitely or going back in time to the beginning of spacetime. According to Roger Penrose's demonstration, geodesics are required to converge and meet their end point in the center of a black hole. When referring to a spacetime, the phrase geodesically incomplete is used to indicate a spacetime that permits geodesics that do not extend continuously. A smooth, albeit somewhat distorted fabric is created by geodesics, which are similar to the grid lines that are found in spacetime. This fabric allows the physical laws to function effectively. The existence of pinched-off zones, which are places where infinities develop and the physical norms are broken, is a consequence of geodesic incompleteness. It was Penrose's contention that singularity is the consequence of geodesic incompleteness to begin with. When it comes to Kerr's objection, which he brings up in the argument, having a thorough knowledge of geodesic incompleteness is fundamentally important. As a result, we ought to investigate this matter more. The mathematical concept that Penrose was alluding to when he said that a geodesic ends in the core of a black hole was one that is extremely precise. As he phrased it, the geodesic parameter is bounded, which means that the mathematical variable that is used to characterize the evolution of something along a geodesic will eventually reach its limit. In the same way that your latitude stops when you reach the South Pole, you are unable to travel any further south after you reach that point. Proper time refers to the time that is measured by an observer who is traveling along the geodesic. This time can be considered the geodesic parameter for the geodesics that characterize the motions of matter, and it is frequently seen as such. Due to the fact that it is not possible to monitor the passage of time along a matter geodesic with a bounded parameter, this would be an indication that a singularity is present. There is no appropriate definition of after the singularity that includes either spacetime or spatial temporal concepts. This is an impasse in the spacetime continuum. In any event, Penrose constructed his argument based on light paths rather than matter ones, and this distinction proves to be crucial, as we will see in the following section. With that being said, for close to 60 years, almost everyone has been in agreement that singularities are necessary for the theory of pure general relativity. As a result of the compelling general argument that geodesic incompleteness is equivalent to a singularity, this phenomenon occurred. Penrose's logic was even utilized by Stephen Hawking to demonstrate that in pure general relativity the Big Bang was also a singularity. All geodesics that are traced backwards in time must converge and end at one place. However, Kerr was not completely persuaded by the argument. A scientist from New Zealand named Kerr came up with the idea for the mathematical description of a rotating black hole in 1963. This description is known as the Kerr Metric as well. This was the second black hole solution to the Einstein equations that was discovered, and it came just 47 years after Carl Schwarzschild's response, which essentially specifies the somewhat less complicated scenario of a black hole that does not rotate. The significance of the Kerr solution lies in the fact that it offers compelling evidence that almost all genuine black holes rotate to some degree. Similar to that Kerr has a major disagreement with both the existence of singularities and the applicability of the Penrose singularity theorem to this particular issue. This is something that should be taken into consideration. It is now possible for us to address his primary area of contention. As I mentioned before, the idea that spacetime pathways terminate due to geodesic incompleteness has led to the belief that singularities exist. This reasoning, however, is not without its caveat. A specific geodesic, the null geodesic, was used by Penrose to build his argument. Objects without mass and moving at the speed of light follow these spacetime pathways. In a curved space, the shortest path between any two points is represented by a null geodesic. When a null geodesic ends, what exactly does it signify? In other words, its geodesic parameter can't grow indefinitely. It must have a limit. We utilized appropriate time to track these typical geodesics when dealing with large particles. But objects moving at the speed of light don't feel the passage of time. Because their clocks are static, the passage of time along a null geodesic does not progress. A new metric is required to characterize the light's geodesic motion. We employ a rather convoluted concept known as a fine parameter to monitor advancement along a null geodesic. Its primary feature is that it grows in a neat and tidy fashion. Null geodesics are proven by Penrose's theorem, which provides strong evidence that affine parameters are constrained within black holes. From this, he deduced that singularities as intersections with no further space in the spacetime grid are inevitable. However, Kerr notes that these affine parameters do not indicate that the spacetime grid collapses at the end of a null geodesic, since they do not meaningfully monitor time. An exponential of coordinate time could serve as an affine parameter to provide a rudimentary example. This function has a bottom-up limit, even though time can take on any value between 0 and infinity. Time does not stop at the limit of the affine parameter according to Kerr. He goes on to say that this disproves the idea that dead ends in coordinate systems inevitably lead to singularities. Kerr's work is entertaining and engaging. He frequently criticizes the physics community for naively believing a conclusion that he calls built on a foundation of sand. His tone is sarcastic, to say the least. A persuasive argument is presented by Kerr regarding the distinct disparities that exist between the black holes that exist in the real world and the idealized ones that are the subject of Penrose's research. Almost all of the real black holes must revolve in some way, even if not every single one of them. Similarly, charged black holes will conform to the Kerr metric rather than the Schwarzschild metric, and the same is true for genuine astrophysical black holes themselves. Both of these metric systems are based on the same principles. It is not possible for a singularity that is comparable to a dot to be present in the core of a Kerr black hole. An extension of the point singularity in the Kerr metric allows for the production of ring singularity, which is a looping strand of infinite curvature. This singularity is formed when the point singularity is extended. Kerr, on the other hand, asserts that this would not be considered a singularity in formal terms. One of the wonderful features of the Kerr metric is that, in contrast to the Schwarzschild metric, the final outcome of collapse towards the singularity is not a required consequence. This is one of the many unique properties that the Kerr metric possesses. The region that is located just below the Kerr event horizon will undoubtedly perish. This is an unavoidable consequence. The event horizon is a path that leads downhill in every direction, and it is comparable to a Schwarzschild black hole in this regard. Having said that, I would not say that in the middle. The gravitational pull of the spacetime's centrifugal force is cancelled out in a revolving black hole, which results in the formation of an inner region of spacetime that is almost normal. After you have traversed the inner horizon of the Kerr black hole, you are absolutely free to travel in any direction, including in the opposite direction. Alright, so please explain the singularity of the ring to me. Kerr is of the opinion that it appears to be a mathematical form of fiction. The gravitational field that is produced by an object that is moving can be symbolized using this way, which is merely a practical method. In addition to this, he makes the implication that the inner horizon would represent the real location of a star that is going to collapse due to its physical stretching. Kerr demonstrates his thesis by demonstrating that not all null geodesics, even with a finite affine parameter, complete at a singularity in the Kerr black hole. This contradicts the outcome of the Penrose singularity theorem, which states that all null geodesics must end at a singularity. He describes families of geodesics that, once they pass the inner event horizon of a Kerr black hole, stop existing and continue to exist endlessly. This means that they are able to follow nearly any path inside the black hole. It was formerly believed that light must pass over the event horizon of a black hole in order to eventually arrive at the central singularity. However, this assertion has been disproved. If Kerr is correct in his belief that the ring singularity in the Kerr black hole is more than simply a mathematical convenience, then this would be a huge development. In light of this, is it possible for us to make any definitive statements on the existence of singularities? Note that the argument presented by Kerr does not indicate that singularities do not occur. Rather, it shows that the conclusions of the proof of the singularity theorem can be misinterpreted. This is something that should be taken into consideration. This remark contradicts the current wisdom regarding the Penrose singularity theorem, which states that constrained affine parameters for null geodesics do not suggest a singularity. This statement challenges the traditional wisdom. The majority of physicists took the position that quantum mechanics would be required to explain the existence of black hole singularities, despite the fact that only a small number of physicists share this view. In light of this, the research conducted by Kerr comes as a surprise. It has the potential to offer a solution to the problem of the singularity before the elusive theory of quantum gravity is completely created. There will be additional research undertaken to determine whether or not Kerr's assertions are true, and we predict that there will be a heated dispute emanating from all directions. Nevertheless, from a theoretical standpoint, there is now less of a reason for us to be terrified of what is contained within black holes. If these objects do not contain singularities, then perhaps we will be able to start formulating theories of physics that are plausible with regard to their internal workings. It is possible that Kerr's most recent theories, which involve a spacetime that is devoid of singularities, will make it easier for physicists to contemplate the possibility of journeying into theoretical space. A heartfelt thank you for being here with us today as we come to the end of our journey at Spaceverse. Your support is what drives our investigation of the cosmos. Remember to hit the notification bell and subscribe to our channel so that you can continue to explore with us. See you until the next time we cross paths in the cosmos.